Okay, over to you, Niraj. Welcome all.
Hello, good afternoon, everyone. My name is Niraj Kale. I have been associated with Salesstrat for more than 5 years, and I have been one of the leading researchers in the Salesstrat. So today I will be presenting in the new architecture or new paradigm that is coming up in the large language models. That is one-bit LLMs. Right. So we have seen the LLMs, most famous one of it being the Chat GPT, and now people are trying to make it more efficient and well, they want to make it more cost effective. So that's why there are new research going on to figure out how it can be cost effective and more efficient. So the new paper has come up from the Microsoft era of one-bit LLM. So I will be giving information about this. So this is introduction to SalesStrat. So this paper was published by the authors from the Microsoft Research and University of Chinese Academy of Sciences with all large language models at 1.58 bits. So, what is a one bit LLM? So, I will directly dive into the one bit LLM part without introducing what exactly is LLM. I hope everyone knows about it. So, in one bit LLM, every parameter is a ternary. That means the parameter is either -1 or 0 or 1. So, that will remove the multiplication operation altogether, and as we are saving the weights and parameters in just one bit, it will be a lot more memory efficient. And also because we are removing the multiplication operation from the matrix computations, that will be more computational efficiency and everything. So, and performance wise, it almost matches with the full precision FP16 transformer model. Also, it is very cost effective since execution time is low and memory required is also very low. So previous works on the one bit LLM. So few days back there was a new concept of one bit transformers. So uh, for that, a lot of research has been done how the architecture is evolved for one bit transformer. So whenever we get the input from the uh, user, so it uses ABS max quantization, and that will convert the weight is to FP8, and it will do the computation using the one bit weights, then dequantization and output. So this is called a bit linear architecture. Now everyone, all of us know what is the architecture of the transformers. There is a multi-head attention and feed-forward network. So here, instead of using the regular linear layers, we use this new bit linear layer. So this will have the Q, K, V values of a transformer, Q, K value parameters as this bit linear layer. So this will reduce these parameters from FP16 to 1 bit. So that will greatly reduce the computation efficiency. Get we increase the computational efficiency. So let's go ahead and see how it works. So
No, no,
normally,
could you go back to last slide? So
yes,
you are seeing on the right, you are showing the usual transformer layer,
yes,
and so it has the FP16 weights.
right,
On the left side, uh, you have been able to compress the weights to 1 bit storage.
yes,
Okay. Okay. So this is the transformer layer now looks like the one on the left.
yes. This is the new transformer layer. so
Okay.
that instead of FP16 weights, we are using 1 bit weight, so that our computing efficiency increased rapidly. So less memory is required and less computation power is required, as multiplication operation is totally removed.
No, but if there's a weight value of, let's say, 65, so that needs an FP16 storage paradigm. Now, how is 65 value represented in 1 bit? So it will be ones and zeros transformation, huh?
Yeah, all the weights are reduced to uh, just 1 bit. So 50, 65. So it is, if it is plus 65, it will be reduced to just 1 instead of plus 65.
Oh, it will be one. It's just
Yes.
positive and negative, huh? One and zero.
Yeah, only these three values are used,
Oh, I see.
minus
Okay.
1, 0, 1.
Okay. Interesting. Okay.
If it is minus 65, it will be minus 1.
Oh, I see. Just binary one or minus one. Okay.
Yeah.
Interesting. Okay.
So normal computations, what will happen? So this is our normal FP16 model. Here we have a weight matrix with FP16 parameters 0.021 296 and minus 0.04. So instead of all this value, we have just 1 minus 1 minus 1 0 minus 1 minus 1 0. So that's it. So this will greatly reduce. So essentially, multiplication operation is removed at all. I mean, first of all, why do we need multiplication in a matrix multiplication? If we have some input x and we have some matrix parameter 2.96, so how we get the output is given over here, 0.2961 into x0 plus second parameter 0.0495 into x1. Like that we get a matrix output, right? So instead, if we have just 1 or 0, we just can put the, it is essentially a signing of an input parameter, so it will just be x0 minus x1 minus x2 plus x3, since it is 1 minus 1 minus 1 and 1. So essentially the multiplication operation is completely removed, so that will greatly increase the efficiency of the uh, our new model.
This is
So
interesting. Now, what is 0.58? I got the 1 bit. Where is this 1.58 coming from?
Okay, so how it works is, so let me open a notebook. Oh, hmm. So okay, so if we have 2 bits, then it is sorry, two values, two values, then it is called 1 bit, right? So 2 to power 0. So now we have three values, 0, 1, and 2. So it is 2 to power, sorry, 2 to power 1. So this will give you 1 bit, two values for 1 bit, right? Now we have three values, right? Sorry, it's the other way around. So it will be, is it square root of, I
Log
forgot that.
and
Huh?
log of 3. With the
Oh,
log of
yeah,
3.
sorry. Yeah, sorry, log of 2. So this is log of 3. So 3 with the base of 2. So that is 1.58 bit. That's why this 1.58 bit thing coming up. So it is basically log of 2 to the base of 0. Sorry, base of 2. Yeah.
Why they are applying log?
Uh, so because this indicates the number of values for a particular bit. Right. Now, if we have 4 bits, right?
140.
Now, log of 4 to base of 2 is 2, right? So, we'll have that many values for that many number of bits, gives you number of bits. So, whatever values you want, you have to take log and give number of bits. Okay. So, log of 3 is 1.58 bit.
So in this slide, um, how can we how we can decide which one will be -1 and which one will be 0? Is like in the row number 3 of your AP16, column number 2, that is
Yeah.
0.104. So in row 3, column 2, you have 0.1304.
Uh, Yeah, so we have basically given the quantization function that will come later. So I'll just explain to you what it is, and we can see what is the quantization. So how the quantization happens is we take the mean of a particular weight, and accordingly to that we will apply this round clip function, max of A, mean of B round. So this will give us our the weight minus 1, 0, and 1. So we'll just come to that a little bit. Right. So, so what is a Pareto movement? Pareto movement is essentially improving our performance with less amount of cost. So, since we are using less number of parameters that will reduce the memory and improve the compute efficiency, our cost is greatly, I mean, reduced, and performance is increased with the lower cost. So that will improve our Pareto movement. Okay, so this is basically high level architecture of the neural network. So essentially, all the weights of a neural network are only -1, 1, and 0 instead of all the floating point 16 that we are using for the weights. So how does the training forward parts happen? So we have the input activation quantization quantized to 8 bits, and then weight quantization before computing the weights are quantized to ternary, and quantized weights are used for the matrix calculations, and result is passed through the activation function. So essentially similar to what we are seeing in this bitlinear architecture. So here we are passing through the activation function, and finally we are getting the output value here. So backward pass gradient loss with respect to output of each layer during the back propagation. So this involves computing the gradient through the activation function and quantized matrix. So although weights are quantized, model maintains the full precision copy to accumulate gradient updates, and this is during the training, because this accumulated gradients may not change the weights immediate ternary weights immediately, but it can change over the time. So that's why this full precision copy of weights is say stored while doing the training of the uh, model. The accumulated gradients are used to update the full precision weight, and after weights are requantized to a ternary format to use in the next forward pass. So essentially, what we are doing with each pass, we are converting the weights to this ternary format, and that is used in the forward pass while doing the calculations, so that our model accuracy is improved, and we are actually doing the back propagation. We are actually able to uh, calculate the error and propagate the error in the earlier layers correctly. So this is the quantization function. So here this gamma. So whatever the total weights are there, I and j, right, in a particular matrix. So what we are doing is it is essentially taking the norm of the weights, means total number of weights, and can calculating by n into m. N and m is the size of the matrix. So we are just taking the average over a particular matrix, and we are calculating the what is the this round cliff function, and based on that we are um, calculating the ternary weight. So is it clear, or do we need to? I think they have given it in the paper,
No,
correct?
no. In the previous slide, you were showing that forward prop, it is converting to ternary weight, and
Hmm.
back prop, when
Hmm.
it is passing the gradient back in the neural network,
Hmm.
it is still maintaining the full precision copy of weights. It's using that, huh?
Yes, that is only during the training.
Okay. So during inference, it will exclusively use the forward ternary weights only.
Yes.
Okay. Got it. So basically, the advantage of one bit LLM would be very deep cost saving on compute power, right? Number of matrix multiplication will reduce dramatically.
I mean, there is no matrix multiplication at all. It's just
Right.
addition and subtraction.
Now it's addition. Yes, yes. Okay.
So Niraj, how much in a metric uh, it'll be cost saving or compute saving, like any percentage or something?
Yeah,
And
they have given. We will come to those slides in a little bit.
how is it? My question is, it's basically like the normal weight values will be ranging between 0 to 1, all the precisions, everything with the precision. Okay, so now we are converting to three values, which is -1, 0, and 1. Uh, so will there be like accuracy, everything will it not affect? It is a huge quantization, right?
Yes, accuracy is affected. So accuracy calculations and all they have given in the paper also. So we'll just come to that in a little bit. So yeah,
So if we quantize this, can we run it on CPU or still do we need a GPU for this?
I think while training we need GPU because as we saw, we still maintain the full precision copy of weights during the training. So inference can be done on the CPU.
Okay, yeah. So it is trained with precision weight, full precision, then converted to ternary weights.
Yes.
I mean, it learns the ternary weights during training, during for forward pass only. For forward pass only, it learns the ternary weights. And
Yes.
then for inference, it will exclusively use the learned ternary weights only because it doesn't need backward pass during inference.
Right. So this is the quantization. Okay, so now there are the comparison with the Llama LLM. So basically, all the one bit LLM are full size that of the normal LLMs, but only since the weights are stored in one bit, the size is reduced drastically. So as you can see, 700 million parameters. The Llama LLM size is 2.08 GB, whereas BitNet LLM size is zero point 0.8 GB. So it's is 2.66 reduction. So similarly, latency, since there is no multiplication involved, so latency is also greatly reduced. And perplexity, that is the measure of accuracy in LLMs, it's almost the same. So here you can see that lower perplexity is better. So here for LLM 700 million a model, the perplexity of the llama is better. But in 1.3 billion model, again you can see the All the memory sizes is reduced 2.93, and again latency is reduced 1.7. And for 3 billion parameters model, the memory of Llama model is 2.7.89 GB, whereas BitNet 1.58 it is 2.38 GB. So 3 point I mean almost 3.5 times reduction. And also as you can see, perplexity is better than that we get in the Llama model. Now let's come down to accuracy. So there are various data sets, RC, HSBQ, and all that. So there, all the data sets, they have tried to calculate the zero shot accuracy. Correct. Yeah, zero shot accuracy. Again, we can see that for 700 million, 1.3 billion, and 3 billion parameters. Again, the 3 billion parameters performance is uh, a lot better, or accuracy is slightly better than what we get in the Llama models. So let's consider latency and memory. So here we can see that BitNet is almost with 70 billion parameter. The performance latency is almost 4.4 times lesser than that of the Llama model. This is in the milliseconds. So yeah, again, on the right side there is a memory consumption in the GBs. Again, the BitNet model is almost one is at minimum is 2.93, one at 1.3 billion parameters, and for 70 billion parameters the size of Llama model is 7 times bigger than that of the BitNet model. Right, so again it improves the latency per memory and the throughput of the model. So let's consider the energy efficiency. So this is considering the 7 nanometer energy cost. So for BitNet model, so it just uses 1 point, sorry, int8 addition, right? And whereas FP16 addition and FP60 multiplication is not there at all. So if we consider the energy efficiency, it's 71 times more energy efficient than the Llama model. So here they have calculated on the various model sizes, like 1.3 billion parameters to 70 billion parameters. The energy efficiency that is actually required is again at least 18 times more, 21 times more, and up to 41 times more for the 70 billion parameter model. So this again they have consider a lot of different data sets and for the calculations of energy. So stable LM and BitNet LM. So 2 trillion tokens. So again, we can see what is the energy efficiency based on the uh, various Grande and PIQA and SciQ and various data sets. So let's see the code of the bitlinear model.
Actually, I had a question.
Yes.
Is the quantization applied only on the feed forward layers or even in the attention?
Yeah. Feed forward is also it's there in the attention layer, right? We saw the BitNet architecture, how the BitNet architecture is performed in the this transformer model.
Okay, so only the feed forward network is quantized, right? The attention is okay.
Yeah,
Even the attention is quantized.
attention heads is exactly not quantized, but yeah, the Input to the attention is quantized. Yeah.
Okay. Okay.
So bit linear transformation is happening for Q, K, V, and even the attention output is going through bit linear transformation. So at various points, you are transforming to bit linear representation. Okay. And pretty much it's a transformer layer. Only thing is you're transforming to the one bit at different points.
Right. So I hope you can see this thing. Now. Normal bit linear, we for bit linear we will just save this number groups epsilon, so register buffer, so wait, so forward pass. So basically, how does bit linearity? We create a group and get the mean of the group, and for mean of the group, we will calculate the alpha, and we will calculate the bit linear as weights. So these are the quantized activation function group. So for activation group, again, we are doing the quantization and calculating the activation. So basically, it is very similar to what we do in normal transformers, but instead of using the uh, normal weights, we are using the quantized weights. So here, actually, it is calculating the quantized weights, and it goes through the linear layer, torch linear layer, and then again goes through the quantized activation group wise function, right?
So this is just the bit linear code. Rest of transformer code remains the same.
Yes.
Okay. I mean, sometimes you feel like, "Dal, why didn't we think of this in a research group? Why didn't we come up with this kind of thing?"
I tried to execute this, but just
So
yeah,
I,
I got the value error over here. I tried to execute the code on the whole app, but yeah, not exactly able. Sorry, yeah, please continue.
I had a question. So have we actually tried a hybrid model where if we know the weights which are actually the most critical weights, we keep them in the normal mode, but only change the rest of the modes. So basically a hybrid kind of a solution.
Yeah, that can also be done. I'm not sure who has tried it. They have not even released their source code. The original authors of the paper, they have not released the source code, but based on their paper, some of the people have created the code on GitHub. But yeah,
Okay, thanks. The other question I had was, using a analog version rather than a binary version. We use a analog model to actually do the calculation. So there, all the multiplication actually becomes an addition. So the
analog
matrix
model means
like we do it in analog domain. This is more on the from the hardware perspective that instead of using bit multiplication, floating point multiplication, we actually do the floating point multiplication in the analog domain because everything is binary here, right? So that's why we use a floating point, which requires a lot of cells for processing a multiplication. But essentially, we have seen an analog domain doing multiplication at
yeah. I mean, uh, definitely we can do this op amp and all that. We can do multiplication using the analog domain. But yeah, I'm not sure if there is any actual hardware that has come out which will act as a neural network in the analog domain. I'm not sure about that.
yeah, we were actually working on a few of those models where we were actually trying to use the analog domain for multiplication. So, but it hasn't scaled to this level. Uh,
Yeah, I guess because I mean over time there might be drift or something. So when their accuracy might affect due to some noise or some parameters. So building actual analog computer has been difficult. So that's why people move to the digital computers.
Yeah, but they're making a comeback. So,
Ah,
uh,
that's awesome. Great.
yeah,
Yeah, analog, if we are able to create analog computers and analog neural network, I mean, that will be almost as fast as our brain, I guess. I mean, very efficient.
right, very efficient. Yeah.
So Neeraj, here there is energy efficiency of very high nature. I didn't get the part of accuracy, decline. So how much is the accuracy decline due to using 1 bit compared to regular 16-bit?
Yeah, they have given the accuracy. Actually, accuracy is in and for LLM model, they measure accuracy as a perplexity.
Okay.
So lower the perplexity, better it is.
No, are you saying this is better than regular LLM?
Yeah. So the 70 billion model parameter, sorry, 3 billion model parameter, the last one.
But I
I
didn't
mean,
get this
Vivek,
part.
it's
How
a
can
slight
accuracy
difference.
increase by losing information? Accuracy is actually increasing.
No, it is not increasing. It is the accuracy is almost the same. Like if you see the difference is very minimal.
Nominal.
Yeah,
yeah, I mean, it's not that great to be honest. Just 10.04, 9.91. So it's
Okay.
not too much of a difference.
yeah. If you think in compute perspective, our energy efficient and all, it is very high. Definitely.
But Neeraj, if this is the case, why would any LLM not use this anymore, right? So, I mean, then it makes sense for every LLM company to start using 1 bit LLMs.
I think everybody will be doing research vigorously now with this new para. I mean, when the paper was out, because people never thought that that can be achieved, but the
Right.
Microsoft has shown that okay, this is possible. I
Mhm.
think Google and Amazon and everybody will be doing research on that, and probably they will come up with their own model in few days.
Correct. That's why the source code is not released, I guess.
Yeah. It's like a weekly race. Every week, which company will outdo the other guy?
Yeah, I mean, just now I read couple of days back the cloud has come with Opus 3 that is actually higher accuracy than the it beat the GPT-4
Yeah.
for the first time. Yeah.
And today we hear that 100 billion supercomputer. And Microsoft and OpenAI are working on a 100 billion AI supercomputer.
Wow.
So you had mentioned that this can be actually implemented on a edge-based device. So what kind of an edge-based device? Because the number of parameters still is around 3 billion, right?
Yeah,
So
but instead of yeah, I mean, I didn't come to the summary. So future we can new hardware can be used. The LLMs on edge-based device can be done. So yeah, I mean, if we consider the memory required here, see. For example, normally if we consider 2.8 gigabytes of memory required for this Llama model, instead of that we can use zero point 0.8 GB of memory, right? So 2.6 times reduction in the memory. So we can definitely use this. Of course, it will not reduce drastically to zero. I mean, memory requirements, but
uh
it will improve efficiently. Efficient means it will improve a lot. As we see, even if we are considering 8-bit BitNet model, still actually we are saving those weights in a 8-bit integer, right? Or I think if you consider the smallest means 32-bit CPU, actually integer is 32-bit. It is not exactly 1 bit. So we have to come up with a mechanism where we saved probably uh, instead of one weight in one integer, we can save up to uh, four weights in one integer, then that will be drastically reduce the memory required. So
Yeah.
we also need to figure out a way to save one means number of weights in a single integer instead of using a number of integers equal to number of weights.
Right. Right.
I think we are close to the era of edge AI. So edge AI is coming fast because if there is a small language model, this is a small language model which is lightweight, right? So that will enable edge AI, whether it's robotics or industrial edge, semiconductor edge, or healthcare edge, so or human body as an edge, or mobile devices. So everything is coming to edge AI instead of cloud. So right now everything needs a cloud round trip, but now LLM can run in the edge itself without needing cloud API round trips.
Yeah,
Yeah,
but
if
it still requires almost around 1 GB. Yeah, if you can reduce it further, then there are these chips now which are actually coming up by Kinara and all that. So
Yeah,
they have a edge based even a LLM can be actually put there, but I don't know whether it'll support 1 gig memory. But yeah, if you can actually reduce it further, then obviously
Yeah, now see if we consider this point 0.8 gigabytes of memory, there are 700 parameters in that, right? So why does it require zero point 0.8 gigabits of memory instead of just 700 million bytes of I mean, because each integer is saved. Sorry, each weight, even though it is 1 bit, it is saved in a one integer. That means it is taking up to 4 bytes, right?
mm,
So instead of saving one weight into 4 bytes, we can take the one weight into one weight means four weights into single. One byte into 1 byte, and in one integer we can directly save four weights. Then we can actually reduce this size to 1/4. So we can actually have this size as 0.2 GB instead of uh, this 0.8 GB. So we have to figure out a way how to save multiple weights in a single integer or single byte.
So looking at the perplexity in the graph, this means that the current language models have a lot of redundancy in the parameters since it can be quantized to like
Yeah,
-1 B1.
yeah, definitely. Yeah, I mean they are huge, right? There are billion parameters, out of which maybe if we consider 5% are not being used, or I don't know what is the 0.5% or 5%, or if they are not being used exactly, then that is huge wastage of memory and compute power, because for inference actually you are doing the computation for each and every weight parameter. So this quantization definitely is useful. I think we have seen that during some of the. I was taking one presentation on the TensorFlow embedded and TensorFlow RT and all that. So there actually, when we do the quantization, the accuracy actually increases sometimes. So
This is really interesting.
it
So the
acts as
perplexity
a
actually decreases in two of the models. That is
yeah
really interesting.
it acts as a regularization parameter. This quantization,
Yeah,
instead of
definitely.
being a
yes, yes.
hindrance, it actually helps.
Yeah, that's a good thought. So quantization actually increases generalization because it will lead to regularized, weight learning. Because if you allow full precision weights, you are overfitting the training data set. But here you are doing approximate weights, so you are actually
Yes, that
increasing regularization.
that is what I thought.
Yeah,
That is what I thought. It actually increases the model. It increases the model
right,
power.
right. So not only it compresses the model, it actually increases your generalized, accuracy. That's very interesting thought. Yes.
Vivek, can you repeat this, what you said? This.
See, basically, if in machine learning, deep learning, we were have facing the problem of overfitting, right? So the solution to overfitting was applying regularization. So regularization techniques involved L1, L2 regularizer, early stopping, a dropout layer in neural networks for shooting some neurons. So you are deliberately damaging the neural network training. To try to make it less overfitted, we were inventing techniques to damage the neural network training, right? Early stopping, L1, L2, weight decay constant. So dropout layer. So now we are here also, we are damaging the neural network by losing weight intelligence by only representing them as ternary weights. So in effect, you are reducing overfitting, and which means it's less overfitted to your training data, and it will perform well with your production data. Because if you allow high precision weights, it will overfit the training data and perform badly on the production data. So here also we are damaging the weights, right? So we are basically reducing the training accuracy, but hopefully increasing the production accuracy.
Okay, more precision means you have a lot of room to wiggle around and capture the noise in the data set. So that is one of the reason, I think.
No, more precision means very accurate weights. So here we are not permitting very accurate weights. We are saying, hold on, I don't want you to cram this. I'm going to give you approximate weights, not accurate weights. So you are preventing the prevalence of cramming. Overfitting means cramming the training data. So it is no longer able to cram because you are making the weights approximate. So it is actually inaccurate. Your training accuracy is going to fall, but your inference accuracy is likely increasing. That's what preventing overfitting means, or regularization.
Yeah, we are allowing to think out of the box, basically. That's
Yes.
Right. Um, so, in summary, we can create this architecture for multiple types of LLMs, like image models or other types of LLMs. And there is a native support for long sequence LLMs. We can develop a new hardware for that. So this LLMs will allow us to, because the memory requirement is very low and latency also is reduced, we can deploy this LLMs on the edge and mobile devices. And again, as I said, we are currently saving this, if you consider uh, one way is saved as integer. So that will be 4 bytes. So instead of that, we can use 4 weights in uh, 4 bytes by, compressing the. So we can compress the weights and save the 4 weights in 4 bytes, or maybe 4 weights in 0.5 bytes instead of using the full 4 bytes. So that will greatly reduce our memory efficiency. So this can be one of the new hardware that can be developed for 1-bit LLMs. So in summary, we saw that 1-bit LLM variant is very parameter is just ternary values. -1, 1 is significantly reduces the computational and memory requirements. And BitNet 1.58 offers substantial reductions in latency, memory consumption, and energy use. The 3 billion model matches the perplexity and end-to-end task performance. So this 3 billion model is almost same as Llama 2 model or Llama model. So this is significant increase in the throughput and drastic energy in reduction in energy consumptions. So future includes mixture of expert models and native support and LLM deployment on the edge and mobile devices. So any other question?
Mixture of experts. We did a webinar in few months, in last 2 3 months.
Yeah.
So that one is like an ensemble learning in for LLMs. So here it is already being discussed in respect with respect to one bit LLM. Huh? So
Yeah, we can because currently all the mixture of experts and everything will require like FP16, right? So we can create a mixture of experts models using 1 bit instead of 16 bits. So that will again be more efficient.
yeah, the new Mistral is mixture of expert. But I was just Googling. I didn't find any LLM being one bit LLM so far. This is still a paper. So
Yeah, they have not released the source code as such.
yeah,
Yeah.
maybe OpenAI will do it next GPTs.
One bit GPT.
Yeah. See, Google Gamma, Google, not Google Gemini. Google Gamma is a SLM. So Google Gamma is 2 billion parameter, but that is more about reducing the number of parameters. Whereas one bit SLM is more about reducing the size of storage. One
Yes.
is reducing the size number of parameter, other is reducing the size of storage per parameter. So two different concepts, but both achieve what we call a small language model or allowing edge AI.
Right.
So I think on the last point, that one bit mixture of experts. So the totality of this expertness, I think, will get a little bit, um, the expertness will be reduced because now once on the quantization function, that 0.04 now becomes plus one, means we are adding information in some places. And if it is minus 0.012, we are making as a minus one. So in some places we are adding information unnecessarily, and so in some places we are reducing information. So information loss is also happening. So
Yeah.
meaning that
When
expertness is now become that much experts. Think in that way also.
yeah. I mean, if you consider 1 bit, then 0.5 is also one, and then 500, sorry,
My give some value as a minus.
500,
Now
500 will
also
also be one. So both
one
these
and
values will be
yeah.
represented as one.
Exactly. So this is the error term. We are adding a lot of error, and also we are if it is minus 500 now becomes minus one. So huge information is getting lost.
Yeah,
Even though
but
in the some generalization happening, but so much being added and
yeah,
reduced.
I understand. But they have shown the perplexity, right? I mean, it's still able to match the performance of the Llama model after all this loss of information also.
Yeah. So are they using the generalized perplexity formula or the same way, or they have some custom perplexity rule?
I think they will have common formula for both the models. I don't think uh, they will have any different formula for Llama and different formula for BitNet.
Hmm.
So this paper came out, I think, within last 1 month.
Yeah,
So I think Microsoft is keeping it under wraps, working with OpenAI on lots of new things. GPT-5 is around the corner we hear, and the 100 billion AI supercomputer has been announced with OpenAI and Microsoft. So these guys are moving, very fast, and they've taken
There is
lead.
a condition. There is a condition on the supercomputer. It will only be applicable if OpenAI comes up with really good models in the future. I read it somewhere.
Okay, okay. So I think the goalpost of state of the art is moving by the week or by month for sure. So by next month, the goalpost will be somewhere else. So the big 10, big 5 companies are throwing a lot of resources at moving the goalpost of state of the art. See, we were debating should we launch a course, and nowadays we feel that the shelf life of a course is like 3 to 6 months, right? So because all the algos will be overturned in 3 to 6 months, so so the shelf life of any AI book or AI course is somewhere from 3 to 6 months. The fundamentals still apply, but things get outdated very fast. So you have to keep doing the next course and next course and the next upskilling and so forth. But good presentation, Niraj. So any other questions, audience? Okay, so thank you all for joining. Kindly fill the survey Honey has floated. Excellent session, Niraj. Thank you.
Thank you all for joining, and yeah, thank you very much.
Thank you all.
Yeah,
Do
thank
fill
you.
that survey, and if you are interested in our new GenAI course, reach out to us.